Hello everyone. For this tutorial video, I'd like to introduce you to vector fields, as well as give a few examples of how you can draw a vector field when you are given a function. A vector field is given its name because it is a diagram or plot of different vectors with different magnitudes and directions, all in one grid. And this can be used to predict things that have many moving parts. They are not predictable with only one vector. For example, the turbulent flow of the wind or the air blown by a fan. The standard notation for the function that gives a vector field is function with vector symbol of x comma y if it's two-dimensional equals p times x comma y times I vector plus q times x comma y times j vector, where I vector and j vector are the x and y components of the vector. And if it is in 3 dimensions, we write comma z in our functions. And we add our third component, r of x comma y comma z times k vector, where k vector is the third dimension, or third component. So if we are told to sketch this specific vector function, we would do it by computing different specific values and then drawing out the x and y components these give. Once we do this, we get a plot like this, but because we are not given a specific limitation for the x and y components, it technically has infinitely many vectors. So as a result, we use a computer program to state that the graph more accurately looks like this, instead of the more tedious method of computing all the vectors manually. We can now discuss the gradient vector field, which uses the concept of gradient vectors discussed earlier. In particular, we remember the formula for gradient vector is the vector of all the partial derivatives as its components. So in order to find the gradient vector field, we would compute the gradient vector of the function, and then plot the vector field of that. For example, if we have this vector field, we can compute the gradient vector field by simply taking the partial derivative with respect to x, comma, partial derivative with respect to y, and then plot the vector field once we have a formula for it. We will explain later on why the gradient vector field is useful when we talk about conservative vector fields and potential functions. Simply know that the gradient vector field exists for now. In my next tutorial video, I will discuss integrals of vector functions as opposed to the double and triple integrals of multivariable functions studied earlier that were not of vector functions. And these are called line integrals because of how a vector function plots out a line, even if the line may be elaborate, such as a helix. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.